So in this video, we're going to talk about terminal velocity. In the last video, we talked about wind resistance or drag, and terminal velocity takes the ideas from wind resistance and drag and builds upon them. So terminal velocity actually is something that affects skydivers. So I'm going to draw a skydiver, and he just jumped out of a plane, and he's falling happily to the earth. This is a free body diagram of a skydiver, so let's draw the forces that act on this guy. The first one is a force of gravity, Fg. And if we remember, the force of gravity can be calculated very easily by taking the mass of the skydiver and multiplying it by the acceleration of gravity. So it's mass times g. Another force that acts on the skydiver is an upward force, which we talked about last video, and this is the drag force, F sub d. And if we remember, the equation for Fd, that's equal to 1/2 times rho, which is the density of air, times velocity squared, which is the velocity of the skydiver as he's falling, times coefficient of drag times the area of the skydiver, the amount of air that he has to push out of his way. So there's these two kind of competing forces. So let's see what happens when the skydiver actually jumps out of a plane. If I were to draw a graph of the skydiver's velocity versus time, we would see the following. So in this here, I'm going to have time on my horizontal axis. The units would be in seconds, but I'm not actually going to put any numbers on this. This is velocity. I'm just going to write VEL for velocity, and that's meters per second. So when this skydiver first starts out, he's going to have this nice linear relationship. And if you remember the spark timer lab that we did, this is what we found. We had a velocity versus time graph that was this linear relationship. And in this case, the slope of this graph was equal to g, which is equal to 9.8 meters per second squared, or meters per second per second. The next portion of this graph, this line would stop being linear and it would actually start to kind of bend over a little bit. Okay? So it's going to bend over a little bit. And in this, what's happening is the drag is getting to be larger and larger. And then eventually we level out and we flatten out that graph. And what we have here, this line, if I was to draw a line across, this is the terminal velocity. So it's actually the fastest that a skydiver can fall as he's falling towards the ground. If we looked at each of these three sections that we just mapped out, we have a short one at the beginning, we have this middle one, and then we have the end. So in this short one at the beginning, we have the force of gravity is actually much larger than the drag force. So we do a double greater than sign to show that the force of gravity is orders of magnitude larger than the drag force. In this next case, the force of gravity is still larger. If we look at his velocity, it's still increasing. So the force of gravity is still larger than the drag force, but it's probably on the same order of magnitude. So force of gravity is greater than the force of drag. And then once he actually reaches this terminal velocity, the force of gravity is equal to the drag force. If the force of gravity is equal to the drag force, what we have is these forces are balancing out, and if forces are all balanced on this person, we could actually say that this person is in equilibrium. It's kind of strange thinking of a person being in equilibrium even though they're plummeting to the earth, right? So they're going at this very high velocity towards the ground, but they're in equilibrium because all the forces are balanced out. So we call this a dynamic equilibrium. And in any equilibrium, what we have is that Newton's first law is actually what governs the motion of this person. So this person is going to just keep falling along the straight line that they're on, going towards the ground. They're not speeding up, they're not slowing down. and they're just going to keep going that way until something else happens. Hopefully he pulls his parachute and slows down. And we call that dynamic equilibrium. We call it dynamic equilibrium as opposed to static equilibrium, which a book sitting on a desk would be under static equilibrium. It's not moving, and it's also all the forces are balanced on it. So with this one, all the forces are balanced, but he's definitely moving. Okay, so let's see if we can take some of this information and see if we can calculate terminal velocity. So like we said, terminal velocity depends on two things. It depends on the force of gravity. I'll draw this one in green because it's the one that's kind of speeding it up. Fg is equal to mass times gravity. And it also depends on the drag force. I'm going to write that in yellow because yellow light is kind of slowing it down. Fd is equal to 1/2 times rho v squared cd A. Okay, so we have these two competing forces. If I drew my free body diagram, get my free body diagram here. Here's my guy, he's jumping out. And he's got an upward force and a downward force. This downward force is Fg, and this upward force is the drag force. Okay, so if we were going to sum the forces on this guy, the net force is actually F net is equal to Fd going up, which is 1/2 rho v squared cd A minus his gravitational force going down, mg. And we know that all that is equal to 0. Okay, so now what I can do is I can subtract mg to the other side. I get 1/2 rho v squared cd A is equal to mg. So what I'm doing is I'm actually setting these two forces equal to each other. Okay, and then I can solve for v. If I'm trying to get velocity by itself, I can divide by rho, cd, and a, and I can multiply by 2. I get v squared is equal to mg, and I have to multiply by 2 on both sides, so I get actually 2mg. And then I'm dividing by rho, cd, and a, so divided by rho, cd, and a. And then the last step is to just take the square root of both sides. So I get that v terminal is equal to the square root of 2mg divided by rho cd A. Okay, so let's see if we can actually apply this. Okay, so let's see if we can find the terminal velocity of a skydiver given these properties. He has a coefficient of drag of 0.5, a mass of 75 kilograms, and an area of 7 meters squared. So as if we were looking at the person coming towards us, the area that they would cut out of the air would be 0.7 meters squared. And the density of air we're going to assume is 1.2 kilograms per meters cubed. It actually might be less if you get up at high altitudes, but for now we'll just assume it's constant density of air. So we can apply our equation that we have that, let's see, the V terminal is equal to the square root of 2mg divided by rho cd A. So if this is just plugging in these numbers, we get that the square root of 2 times the mass is 75 kilograms times g is 9.8 meters per second squared divided by rho, which is 1.2 kilograms per meter cubed times 0.5 times 0.7 meters squared for the area. So if I was to actually go ahead and calculate this, I can pull out my calculator and I'm going to get the following. See if I can do this in a place where you can see it. So I get that going to type the square root of 2 times 75 times 9.8 divided by 1.2 times 0.5 times 0.7. And I find that I get 59.16 meters per second. Now, one thing I always like to do, especially when we have speeds in meters per second, is I like to think about what that actually means in terms of miles per hour, because I have a much more intuitive sense of what miles per hour are instead of meters per second. So the conversion factor between meters per second, 1 meter per second, is actually equal to 2.2 miles per hour. So if I have 59.16 meters per second times 2.2 miles per hour divided by meters per second, I actually get that this is equal to about 130 miles per hour. So this person is certainly going pretty fast as they are falling down towards the ground, and they're going to be relying on their parachute to slow them down eventually. So that is terminal velocity.